Hi, doctor. How's everything going? It's an honor to have you here. This is Hank, and next to me is Back. And today we are going to interview Dr. Kyzivat, now from Harvard University, in his postdoctoral program. Can you briefly
Thanks for having
introduce
me.
yourself, doctor?
Yeah, my name's Ethan. Thanks again for having me. It's a pleasure to speak with you all and talk to some young scientists, which I was not too long ago. And my background is very interdisciplinary as a physics major, an earth science PhD. I've worked in water quality, and the common thread in all my research is remote sensing. So using satellite and airborne measurements to study the earth. And now I'm working on methane emissions from natural and human sources.
So can you introduce more about Earth physics? What do scientists usually do in this field?
So earth science is a really broad umbrella of fields. Um, it includes people who study the geophysics of the interior of the earth, of fluid flow, our magnetic field. It includes people who study all layers of our atmosphere, from the boundary layer that we sit in right now to the upper atmosphere and what's called the near space environment. So aeronomy, it's called. So the space weather of the upper atmosphere. There's people who study living things on Earth through the lens of earth science, and those would be more like biogeochemists, which is itself an interdisciplinary term. People who study the relationship between life, the natural elements in our Earth, and the chemistry and how they interact. People who are studying microbes in the ocean, various forms of oceanography, physical oceanography, chemical oceanography, biological oceanography, and then people who study the actual Earth's surface, which is also where we live and where much of life inhabits. So people who study water in the atmosphere, how it flows through the land, how it reaches the ocean, how much is there, what's in it, and people who study the forces that change the shape of the Earth. So those are the geomorphologists and the geodesists, people who are making measurements of how round the Earth is, how its orbit is slowly changing over time due to tides and the solar cycle, and due to the positioning of mass on the Earth's surface, such as ice sheets and continents, which change over time, right, with continental drift. All of these things can have effects on the Earth's rotational speed, which I find very interesting. So Earth science really encompasses a lot of the fundamental sciences of physics, chemistry, and biology, but as applied to Earth and also to planets. So planetary scientists do all these sorts of things, but with way less data and with typically the planets in our solar system, whereas astronomers might be studying larger objects like galaxies, and maybe exoplanets. I'd say planetary scientists and astronomers both kind of have exoplanets are under both of their purview. Typically, planetary scientists will be using more orbital data and rovers, whereas astronomers can only use telescopic measurements. Maybe that's kind of a working definition between the two.
So technically, the way you differentiate an an Earth physicist and a planetary scientist is that a planetary scientist usually have less data and they work on, the more macro and less detailed um phenomenon going on planet.
Yeah, I would maybe wouldn't say less detailed, but I think that the different way of thinking between an Earth and a planetary scientist is that as an Earth scientist, you have more data than you can know how to work with. Even though we're still limited with data, we have a lot of it for various areas. And we have a lot of orbital remote sensing data that I talked about earlier as a remote sensing scientist. And planetary scientists are very data scarce. I mean, we've never had a sample return from Mars. We only have asteroids that we think have picked up that have originally originated from the same source as Mars. We have sample return from some asteroids now, which is very cool, but we're talking about grams of sample. So they're very limited in data. And of course, the whole history of the planetary bodies they're studying they can't take cores like the same way we would take a sediment core in the ocean that goes back millions of years. So I think you're right that the difference is a different way of thinking and how to work with limited data and to make models that are designed to work with very limited data. And I mean computer models. Yeah.
So I'm really curious about the thing that initially drives you into Earth physics. Like, oh, how did you get more interested in this field in the first place?
I always knew I wanted to do research around the environment and climate change, which is the big issue of my time when I was growing up, and I think it still is, maybe even a bigger issue now. um, and I was interested in physics because I liked thinking about how things work, both human-made objects and natural objects, how things seem to follow these laws that no one wrote. They're just kind of the laws of the universe, the laws of physics. And I was very interested in that. Um, and I realized that a good environmental application of this knowledge is to study the physics of the earth. So that brought me into while I was an undergrad, I did my senior research in a geophysics lab where we were making a laboratory model of the Earth's geodynamo, which I alluded to earlier. That's the liquid outer core of the Earth is made of iron, which can hold a charge, and it's rotating due to the Earth's rotations and due to convection because it's very hot and it's not uniformly hot. And this gives rise, scientists think, to our magnetic field, which hasn't always existed in the history of the Earth. And it's also changing. So I think it's 1,000 years or so. Actually, yeah, I don't remember the number exactly. There's what's called a magnetic pole reversal. Have you all heard of that? And the suspicion that it might
Uh,
be happening now? Yeah.
yeah, yeah. I think it's I heard that like it's coming, it's soon. It's coming, uh, like 5,000 years around. Was I don't know. Yeah, it's the poles are gonna change soon, I guess.
Exactly. So the Earth has a rotational North Pole, which is the imaginary axis that the Earth's spinning on. That's 23.5 degrees inclined away from the what is it, the ecliptic plane. Um, there's also a magnetic North Pole, which is similar to it, but is not so easy to identify because it's moving, and that has to do with the distribution of charged particles in the core. And as you said, I think it's maybe every 5,000 years or so, the polarity switches. So north becomes south and south becomes north. And oftentimes this is preceded by a period of very fast pole wander where the magnetic declination angle, which is the difference in degrees between true rotational north and magnetic north, starts to change very rapidly. And that's what we're seeing now. The North Pole's moved something like 100 kilometers one year, 50 or 100 kilometers, which is very, that's fast. I mean, that's probably like as far as I don't know, a very immobile person might walk in a year. And so the pole's moving farther than some people might walk. And so anyways, this is happening now. And so some scientists have thought it's indicating that the poles are going to reverse, which would be really challenging, both for map and compass navigation, but also for more like digital navigation instruments that rely on polar north. Of course, now GPS provides a good alternative to that. But it would still be confusing to people, and let alone animals who might have magnetic sensory input to help them with their migrations. So that's a long tangent to say I was working on a project that was trying to simulate the Earth's geodynamo made out of metals that are easy to work with, that you don't have to heat up to unsafe temperatures. So we used two metals called gallium and indium that are both liquid at slightly warmer than room temperatures. So you could put a piece of gallium in your hand and your body heat will melt it. And it's safe to work with. Although you do have to keep it inside of an acid because it'll just start oxidizing, basically rusting within seconds. So I was making all these mixtures of liquid gallium which is not magnetic, and adding to it iron particles of various sizes and aspect ratios to give it magnetic properties. And we were also measuring what's called the rheology, which is the fluid property of how compressible it is, how much surface tension it has, how much viscosity it has, how thick it is, to try and simulate what we think the Earth's core is. So then if we have a functioning model that we think is accurate, then we could do all sorts of experiments on it that we could not do on the actual Earth's core. And we could do it way more cheaply than if we were using actual liquid iron, which you couldn't really put inside of a university lab building unless it was like this much. So that was my first experience into the earth science. And as I said, I was interested in environmental applications of it, which led me to a PhD program in remote sensing of hydrology and thinking about how the waters on our Earth are exchanging with the atmosphere, including with greenhouse gases. And that kind of led me to where I am now. I've kind of abbreviated the last part, but we can talk more about that, I'm sure, later.
Oh, I have so many questions about what you have just said. So you mentioned that for your undergraduate experience, you work in a lab that works on something that is in the inner part of the Earth. How do the scientists actually carry out measurement to know what is actually going on beneath us, so many kilometers away?
Great question. And maybe you'll like the answer if you're interested, if you both are interested in physics. The way that we can image the inside of the Earth is through seismology. So seismology is measuring the vibrations that are happening to the solid Earth. And what do you think might cause vibrations of the Earth? Basically sound waves. What do you think might, if you put your ear to the ground and you heard sound, what might be causing that?
The motion of the
chemical reactions.
And motion of like the ocean, or the ocean tides can cause vibrations, waves. If you're right next to the ocean, you'll hear waves. If you're right next to a highway, you're going to hear trucks going by. So these seismometer stations are usually situated in somewhat remote areas, so you don't get urban, basically noise pollution. Chemical reactions is interesting because the center of the Earth is very hot, right? Super hot. I mean, maybe like 600 degrees Celsius, maybe even hotter. You can't even, the deepest we've ever dug a mine is, I think, around 2 miles. And it was probably like 40 degrees Celsius down there. It needs to be constantly air conditioned. It's very hot in the Earth. And why is this? The Earth was formed, we think, by collisions of protoplanetary bodies, and one of those spun off and became the moon. And these collisions were like massive atomic bomb explosions. So the whole Earth was liquid magma for millions of years, or maybe, yeah, millions of years. But then it cooled on the outside. So why is it still hot on the inside 4.6 billion years later, which is today? And scientists think that part of it is because the heat is actually self-sustaining due to nuclear decomposition reactions of common elements like potassium. So someone told me recently that you get more of a radiation dosage from a banana than you do from a dental x-ray, which I don't quite believe. I think that they're probably similar in magnitude. And that's because bananas and lots of fruits and vegetables have potassium, which is an element that's found in the Earth's core or in the Earth's interior, in the crust, and then of course in our soils. So it ends up in a lot of our food. It's a nutrient that we need. And there's a naturally occurring radioactive isotope of potassium that's slowly decaying. And so this is part of our background radiation dosage, which is, radiation is not great for your health, but the background is very little. Most of our radiation dosage comes from, or a lot of it comes from things like flying, exposure to X-rays, which are getting safer. But anyways, so there is background radiation in a lot of the materials around us. And so this radioactive decay of potassium, as you said, is a chemical reaction that can heat up the Earth. And so some scientists think that this is why the Earth's core remains hot even after all these millions of years. It hasn't cooled off yet. It's because there's chemical reactions that are exothermic that are producing heat. So that was another long tangent. I love going on tangents. That is to say that the Earth is making sounds. And what about the largest sounds, the largest rumbles we might hear in the Earth? What's causing those?
Earthquake.
Volcanoes.
Absolutely. Earthquakes and volcanoes, absolutely. And on Mars, which does not have tectonic plates, it did at one time, and then they stopped. And that's kind of an active question, why the tectonic motion stopped on Mars. That would be very bad if it stopped on Earth, because it would mean on the long time scale, there's what's called the rock cycle, where elements over millions of years are transported along plates, and they go into subduction zones, end up under the ocean, and they end up in the mantle where they melt, become homogenized, and then millions of years later, they emerge back out on the surface through magmatism and volcanoes, and whether it's from magma or an ash plume. And so on very long timescales, our elements are all cycled through tectonic plates. So even things like landfills, I sometimes think about this. Basically, there's no plan for some of the heavy metals in a landfill are just going to be there forever. I mean, and some of the terrible stuff we put in landfills is never going to go away unless you wait long enough and wherever your local landfill is makes it to the next subduction zone and ends up inside the Earth, totally gets melted and incinerated, and then it'll come back out refreshed. So that's the 100 million year timescale solution to waste. But anyway, Mars does not have this.
Yeah.
So what's making Mars vibrations on Mars, what are called Marsquakes instead of earthquakes, are micrometeorite bombardment. So, and also real larger meteorites, talking about things like the size of a pea that are flying through space. They hit the surface, there's no other sound, and that gets picked up by seismometers on Mars. The wind is also, because these instruments have to be so sensitive, winds can cause enough vibration that it's detected in the ground. So through seismic imaging, in answer to Hank's earlier question, seismic imaging is how we know the composition of the Earth all down into the core and back out the other side. And that's because if you think about your physics of waves that we talked about in our class last summer, waves propagate through mediums at different speeds. So the speed of light is a standard 3 times 10 to the 6 meters per second, right? Is a standard, is a physical standard, but that refers to the speed of light in a vacuum. So the speed of light actually changes very slightly when it goes through different mediums, and that's why glasses work, because our different materials have different indexes of refraction, and it's not affecting. We can't perceive how it's changing the speed of light, but what we do perceive is that it can bend light. And I read about labs that have actually designed materials that can slow light down to like the order of millimeters per second or centimeters per second. Essentially, you can trap light in very fancy laboratory-made materials. So anyways, seismic imaging uses this property that sound waves travel differently through different mediums of different densities, and whether they're solids or liquids. So if you have enough seismic stations throughout the world, which the US is chock full of them, and I'm sure China is too, and other parts of the world, not so much. And you hear an earthquake that originated, let's say here in Rhode Island, United States, how long does it take until seismic stations in China pick it up? And does the one in the eastern part of China hear it at the same time as the western part of China? And what is the frequency and the amplitude of these waves? And basically looking at all the paths that the waves have made through the Earth and the arrival times, you can figure out the density of the materials and whether they're solid, especially whether they're solid or liquid, because that makes a huge difference. Sound wave travels a lot faster in a solid when the atoms are bound up in a lattice than in a liquid when they're moving around.
Oh, okay. So mention earthquake, and then you also mentioned the word Marsquake. Is that an actual word among
Yep.
scientists?
Yep.
Oh, okay.
So
That's really
there's
cool.
also Venus quake. Like,
Venus quake,
is
sure. I've
there
never
such
heard.
things like for every planet?
Yeah, sure.
Oh, wait. Actually, I just thought about something interesting. So because Earth, Earth, uh, some part of the Earth structure is solid, so we have earthquake. But for the gas giant, they probably do not have similar geological motion, right? Because there are no solid stuff inside.
But they definitely still have waves. And even our atmosphere has waves. The same way the ocean has waves that you swim in, it also has waves of much longer periods. And those would be more like ocean swells that happen on the order of minutes and hours. And our atmosphere has waves. So, in fact, we have in my lab at Harvard, we have really sensitive pressure sensors on the roof of the buildings where we have atmospheric stations. And when there is a massive explosion type event, like when a meteorite, a few years ago, a meteorite like exploded over Russia and made the news and was kind of had some kind of big explosions, that caused a pressure wave that slowly propagated throughout the whole world. And at our station in Cambridge, Massachusetts, it was detected by a slight blip in pressure. And a number of hours later, they even detected the wave again as it made its way back around the Earth. And you can even see animations of this in satellite measurements that show that you can see the wave propagating because it's changing. I can't remember exactly what it's changing. Maybe it's causing clouds to move slightly or condensation to happen. But you can see pressure waves from like a extreme event like that. There's also natural waves, standing waves that just build because of the fact that the atmosphere is enclosed. It's a circle. It's essentially bounded. Um, and so there's standing wave patterns that can form that are actually one of the more efficient ways of transporting matter and energy throughout the atmosphere, or not matter, but energy and momentum through the atmosphere. So absolutely the gas planets would definitely have waves, but certainly not solid earthquakes.
Okay, so in terms of the structure of the Earth, like how many theories are we like what percentage of the theory are we really sure about? Because in theoretical physics, there might be lots of theories that are simply based on some hypothesis that people do not that do not really have evidence for. Then what is the situation in Earth physics?
Good question. I'm not the right person to ask on different theories of the structure of the Earth. I think that's actually pretty well understood. There's good consensus on it. I went to a talk once from the person who first proposed plate tectonics, the movement of our crustal plates. And that wasn't discovered until the 1950s. So before then, people had no idea why there were earthquakes, why there was volcanism. They couldn't explain why samples from very cold modern climates had fossils from very warm temperature organisms. And the theory of plate tectonics, which move about as fast as your fingernails grow, about a centimeter a year, can explain why we might have tropical bird fossils up in northern Canada. It's because if you multiply that 1 centimeter a year by many, many years, you can get to a warm climate. And so I think things like plate tectonics, the structure of the Earth, are much more accepted or are consensus. There's not a lot of there's no need for alternative theories. Questions about the early Earth history, though, are still very much out of the open. Like, when did plate tectonics start? Was it stronger or weaker back then? The question I mentioned earlier, what is the source of the heat in the interior of the planet? Does Mars have a similar heat gradient? We've never drilled down into Mars. The deepest we've drilled is maybe like a few meters. There's an instrument on one of the NASA landers on Mars that's done that. And I think it actually hit a rock or something, so it couldn't go as far as was planned. Yeah, other big question. Yeah, I mean, the early Earth, when did life form? What were the conditions for early life? Was it really, how did nitrogen first get fixed? Because nitrogen is only usable by life if it's in what's called a fixed form, which means compounds that can be uptaken by life. And atmospheric nitrogen is elemental nitrogen, N2, which is inert to almost everything, including us. I mean, we're breathing it in right now, but we can't absorb it or anything in a meaningful way. And so what caused those nitrogen fixation reactions? People think it might have been lightning, but all of this is there's, again, this is when Earth science becomes more like planetary science, where we're very data limited. There's very few rock samples that have even survived. The oldest rock samples, I think, are around 4.2 or 4 billion years old, which is very old, but they only come from like two parts of the world, in central Canada and parts of Australia, where we have very old portions of the Earth's crust that have not gone through that rock cycle I talked about. There's just because it's kind of random, it doesn't hit every part of the Earth's surface doesn't always recycle every 100 million years. So there's some parts that have survived, but only limited. So there's a lot of uncertainty around the early Earth.
Okay, that's really interesting. So let's now go back to your own research project that you are working on. So now you are mainly focused on methane, right?
Yes.
So I Googled online and I found that it's the second most significant greenhouse gas, following carbon dioxide. And I'm just wondering how do scientists evaluate which kind of gas is the most dangerous greenhouse gas?
That's another great question, Hank. It all has to do with what's called radiative forcing and radiative transfer. And that is a very astrophysics phenomenon that is encountered by both of our fields. That has to do with how do different gases interact with light as it comes in. And so the greenhouse effect, as you may know, is due to the fact that our atmosphere is transparent in what's called the short wave of light. And I can show some slides actually I have on this if you're interested. But you're probably
Sure.
familiar. Yeah.
Can you share the screen?
Yes, I will in a second. Yeah, I don't have one on the greenhouse effect, but I do have this electromagnetic spectrum, which is the heart of remote sensing. Here we go. Share screen. So this is a graphic from NASA that's showing the electromagnetic spectrum of various waves, also known as photons, that have different wavelengths. The longest waves are radio waves on the order of 100 meters or kilometers. And on the high energy side are the gamma waves, X-rays, which are used to image the body because they have such high energy that they can penetrate through various matter. And shown here in the gray is the absorption spectra of our atmosphere. So when the gray bar is high, that means that it's fully absorbing and the atmosphere is considered opaque, which means that if you shine a light with this frequency, it's not going to make it through the atmosphere. And that's, thank goodness, right? Because these are the dangerous radiation that's going to give us skin cancer and sunburn. You'll notice right here in the ultraviolet range is right when it starts to drop off. And this is why we still get sunburnt a little if you're out for an hour or so. And you'll also see here that this is what's called an atmospheric window, meaning the atmosphere is transparent. And it's no coincidence that these are the wavelengths of light that we can see. We can see the visible light spectrum, which happens to be right, and it's not a coincidence, it's right in a transparent window of the atmosphere. What would happen if we could only see in the far ultraviolet?
What could
How far
happen?
would we be able to see?
Um, not far, I guess.
Yeah, we'd be basically in fog all day long. So that's why living organisms have adapted to use these wavelengths. And also, I think it's pit vipers can also sense the thermal infrared, which is out in this range. And you can see there's a few windows here as well. So if you're sensitive to the thermal infrared, it would make the most sense, and I'm sure this is how they've evolved, is to be able to see in these wavelengths of infrared. So the atmosphere is mostly, and so the sun, now I'm not sure if this is a coincidence or not, but the sun actually emits mostly in the visible light, visible ultraviolet, which also happens to be the transparent window of the Earth. And that's a little bit, I'm sure there could be a whole study on whether that's a coincidence or not. But as far as I'm concerned, it's a coincidence that gives rise to our greenhouse effect, because the short wavelength light makes it right in through the atmosphere, no problem, until it hits the Earth. And that's when it gets absorbed by the solids, our Earth's surface, and they heat up and they get more energy, and all vibrating molecules are radiating energy, right? Unless it's at absolute zero. But do they radiate energy back in the same wavelength? Do they radiate higher energy or lower energy? Well, because of thermodynamics, they're not going to send back more energy than they got. So they're radiating at a lower energy, so higher, longer wavelength part of the spectrum, which is, for temperatures that we're familiar with, that's what's called the thermal infrared. So that's why people associate infrared with heat. Basically, all of these wavelengths can be associated with heat, but it's just that objects of around 20 degrees Celsius room temperature emit in the infrared. An object as hot as the sun is going to emit in the visible. And you'll notice that most of the infrared is an atmospheric opacity, which means that these emissions are not making it right back out into space. They're getting trapped by our atmosphere. They're heating up the molecules in the atmosphere, which in turn are radiating it up and down. So we have this feedback loop, and that's the greenhouse effect. And so the way that we can study gases and figure out which one contributes most to the greenhouse effect is we can make these plots of their transmission or absorption spectrum, whatever you want to call it. And they're very different for different gases, depending on, it gets down to molecular bonds, because these absorptions are due to the different ways that molecules can receive energy. A molecule like methane, CH4, can vibrate in a particular way because it's got 4 hydrogens sticking out from it. And that gives rise to a unique absorption spectrum. And so if you measure these gases with what's called a spectrometer, which I can talk more about, that's an instrument used by both astronomers and earth scientists to study the properties of gases and solids. You can basically measure the efficiency at which light can pass through that gas. And it turns out that for methane's about 100 times more effective at blocking thermal infrared than is carbon dioxide.
Oh, okay. That's really cool.
Mm.
So okay. So there are people who say that climate change is caused by mainly human activity, and there are also people who say the core reason of climate change is that we are now at the end of a geological period, and and it's kind of natural for the climate to change. So from the perspective of a scientist, which side seems to be more valid?
Well, you said there's some people saying that climate change is a natural phenomenon. So the climate change we're seeing now, if the people who say that are not the scientists. So it is scientific consensus doesn't mean that 100% of the people agree. It just means that it's the theory that has the best evidence for it and that is most widely adopted. And the theory of human-caused modern climate change is very, very, very widely accepted among scientists. You will be hard-pressed to find serious scientific criticisms of it. But of course, as we talked about in our class, that's part of the scientific process, is being critical, reevaluating when new data comes in, and being open-minded to what you see in observations. So it's good that there's the potential for debate, but most of the people, especially in the year 2024, who are repeating this narrative that the changes in the climate that we're seeing now are just due to the fact that we're emerging out of an ice age or natural climate variability or the solar cycle, something like that, that is not based in scientific evidence or consensus. So the International Panel on Climate Change, the IPCC, is a really unique organization because it has basically, the world's scientists have delivered on a globally governed scientific body that involves dozens of countries, probably like up to 100 countries, scientists from all these countries that meet every 5 years or so and spend about 2 years writing a volume. I can show you how thick it is. Oh. I'm sorry, I can't find it, but
No worries.
writing a report about
No
this
worries.
thick every 5 years. That's a synthesis of all the hundreds of studies on climate change, including studies that are reanalyzing the radiative transfer equations that I just showed you. And that number I said, like 100 times more effective than carbon dioxide, that number changes slightly every few years as people get better and better instruments and can more precisely quantify. It doesn't change drastically, but it changes a little. And so this is the scientific process, is deliberately looking at this question and reevaluating as new data comes in. And one of the things they study is the solar cycle, because that's one of the criticisms from some of the anti-human climate change people, is that the sun actually varies naturally in its brightness on the order of, I think, 10 or 100 years. And in fact, this summer is a really high solar activity summer. I think that's different from the solar cycle, where it actually is brighter or darker slightly over time. And they found that that's only a very small part of the radiative balance of the Earth. It's around 1%. So 1% of that budget is changing over time. It might be getting warmer or cooler. The radiative forcing from carbon dioxide and methane might be 50, 100 times as strong as that. And that's what's changing over time significantly. So that's one argument. I'll briefly say the other argument is that, yes, we're coming out of an ice age, which happens in this geologic period that we're in now, called the Holocene. We've had ice ages roughly every 100,000 years. And it's been about 12,000 years since the last ice age ended. So without human activity, the Earth would have been warming. But we've got a lot of examples of previous ice ages and how fast we've warmed out of them. And the amount of warming now is unprecedented in millions of years, not just 100,000 years. So this sort of warming would be really anomalous if it was just caused by the forcings that cause an ice age.
So suppose that we do nothing about the climate change at this point. What is going to happen in a few years?
Well, in a few years, what's happening now is going to keep happening. And in some parts of the world, that's not a lot that you can observe. But in the Arctic, where I've studied, that means rapid permafrost thaw. Landscapes are totally changing from being dominated by permafrost, which can only support a small number of trees and vegetation, to these thawed permafrost environments that can support a whole different sort of species. So it's changing ecosystems entirely. In terms of the southern parts where more people live on the planet, it's causing heat waves, it's causing droughts, and the wildfire seasons have gotten really bad in the US the last few years. I don't follow how it is in China, but I'm sure that there's areas where you get wildfires, and those are caused by basically climate. The heat and drought and wind is what sets you up, and a spark, which is usually caused by people.
Yeah,
Fireworks.
There was also one really serious mountain fire. I think it was last year. in one province in China. So yes, it is, yeah, because like I remember that last year's summer was especially hot. So it's getting really weird these days.
Yeah, it's now become very normal. And it wasn't when I was growing up, but it's normal now to be in the summer to be smelling smoke caused by fires thousands of miles away. Um, Based on the wind circulation in the mid latitudes where I live, and I suppose you do as well, winds are typically blowing from west to east. And so the western part of the United States is where it's very dry, especially in the summer, and in Canada as well. And so these fires are causing air quality problems thousands of miles away, and you can smell it. You walk out of the house and you're like, "Ooh, that smells like a campfire," but it's not. And so
Oh,
So
this
it's
is,
camping.
yeah, bad for air quality and health.
okay, so since the scientists and the government are now taking active action, then then is everyone's goal to stop the heating process, or are we even able to reverse the process to the extent that the temperature will actually go down a little bit to its previous standard?
Another great question, Hank. Um, so the IPCC, this international body that studies climate change, also makes recommendations on what's called mitigation of these effects. So they talk about the physical science behind climate change, how it's happening. They talk about um, mitigation of what we can do to prevent it from happening further. And then they also talk about adaptation, which is some of these changes are basically permanent on the order of human lifetimes. We've already going to have to live with these fires. They're not going to go away. So how do we change where we live, how we live, the technologies we use for energy and et cetera? How are we going to adapt? And so the goal set by the IPCC to avoid extremely harmful changes is 1.5 degrees Celsius. Well, I think they've set 2 degrees Celsius of mean annual global temperature, and 1.5 degrees Celsius is basically the best possible target. And every year they publish how much of our energy needs to get shifted to renewables in order to meet this goal. And every year we don't do enough, and so they change the estimates. And it's now looking like it'll be challenging to meet the 1.5 degrees Celsius goal. But there have been a lot of international climate summits focused particularly on this question. How can we stop emitting rapidly enough? We know the Earth's already warming, it's going to warm some more, but how do we limit this to the less dangerous levels of 1.5 degrees Celsius? And in order to do that, you have to think about methane. Because carbon dioxide is pretty inert. Once you emit it into the atmosphere, it stays there for hundreds of years. A lot of it gets dissolved in the ocean. Some of it ends up back in trees, which are fixing carbon. But the CO2 in the atmosphere just stays there. Methane actually naturally is broken down in around 9 or 10 years. So if we stopped emitting methane today, all the sources shut off, in 10 years, it would be out of the atmosphere. Which is and if we want to cause rapid prevention of climate change, that's a really important thing to do. So that's why methane is a big target right now, is because the effects will be lasting, and a lot of the sources are decoupled from our energy sources. So that's things like wastewater plants, landfills, oil and gas extraction that's just leaking methane into the air. All these things can be fixed with basically by putting caps on it or adding biological reactors that break it down. And we don't have to fly less, drive less, carpool, take the train, all these things that people find difficult. Or switch our power plants to work on renewables, which is expensive. So that's why methane is a really appealing target for policymakers.
I feel that the situation of climate change is sort of really similar to the development of AI, because when we were first developing AI, everyone tried to speed up, and then when there's ChatGPT 3.5, people like Elon Musk they started to allocate for the pulse of the AI development, and then for climate change it seemed to be the same case, because there was industrialization, people are emitting pollutions, and then scientists are now trying to mitigate the impact of this. Do you feel that this is something that is really common among all technological development?
That's a great comparison. I think that this is why we have governments, is to think about the collective good. And whereas from the mind view of a company, more is always better. More technology, faster, more subscribers, more demand is always good. And if you're thinking about a collective mindset for the whole world, and even governments don't really do this. They only think about their portion of the world, their people. If you really think about the whole global world, then suddenly what seems like progress is actually harmful to a lot of people. So climate change, obviously, in the early 20th century, when people got cars, that was progress. It brought a lot of good to people's lives. And they didn't know at the time that they would be impacted, and particularly parts of the world that even today don't have a lot of cars are suffering the consequences of the energy consumption of the wealthier parts of the world. And so it's zooming out and having that global worldview is when these things never seemed like a good idea in the first place. And ChatGPT and AI is obviously, there's a lot of people worried about the consequences of it. And the companies who are making it are also worried about it too, but in the end, they can only profit if they're selling it to us. So they're going to have a different perspective than someone with a national level worldview or a global worldview, thinking about, well, how is this going to benefit or hurt us in the long run? Our ancestors and our fellow citizens of the world who are living in places where they don't have computers, let alone AI.
Then do you feel that for individuals, is there something like a moral obligation to work and contribute to the mitigation of climate change?
Great question. So you've probably heard of the concept of a carbon footprint. That's
no.
okay. So that's the idea that our actions, our choices in energy and consumption and lifestyle and food all have a cost in terms of, well, obviously money, but also in land use, water use, and the amount of carbon released to the atmosphere. And there used to be this notion that we're all responsible for our own carbon footprints, and that if we want to be good citizens to the world, we should do things like making choices that use less carbon. So as I mentioned, flying less, sharing a car, biking instead of driving, using efficient heating and cooling technologies, using renewable energies. And these are all great things to do for the planet. But if we expect the sort of rapid and extreme change we need to make in order to meet this 1.5 or 2 degrees Celsius target, we're not going to do this if everyone just decides to be good. Because oftentimes being good in this sense is the more expensive choice. And people have a lot of needs with their own personal choices and resources. And you just can't expect the whole world to act in this altruistic way. And so this is where I think the role of governments and companies and larger organizations, they have the primary responsibility to address these issues. So right now, the energy that I pay for, I can pay a little bit more and get solar energy. But most people are trying to save money on their energy bills. And you can't expect everyone to choose to pay a little bit extra each month to get a solar powered energy. What you should expect is that the government can step in and subsidize the renewable energy, which it is doing, but it's still a little bit more expensive than fossil fuel energy. So you can't expect change to happen unless large players like the government step in and allow people to make choices that give people the opportunity to make the choice that will have an effect on the climate. And of course, the number one thing we can do to stop climate change and to prevent it is to switch our energy source. away from natural gas, coal, oil, and towards solar and wind, and in my opinion, nuclear.
So finally, let's go back to yourself. I know that you are really interested in jazz and playing piano. So did you feel that there is a connection between jazz and physics in general?
Absolutely. You saw that I was very interested in the book, The Jazz of Physics, written by a Brown professor whose name is escaping me right now. And he talks about how waves and vibrations are so fundamental to how the universe works, and also to how the body works. Our neurons and our nerves are sending electromagnetic waves, just kind of like wires. And that's an analog signal, not digital. So we're analog instruments essentially. And so I think the connection between jazz and physics is the study of motion, basically of time and motion. The passage of time and the way that we experience it, the different colorations to how we can experience time passing when there's one type of music versus a different type of music. Yeah, in a few words, that's what I would say the similarities is. I would also say that the reason I like listening to jazz is because it kind of makes the same sound that my brain makes when I'm not thinking about anything. It kind of it tickles the neurons in the right way. You know, whether I'm listening to it carefully or listening to it as a background. And both types of listening are valid. And there's also kind of an intuitive way that we perceive music and an intuitive way that we perceive science, which is very important. And there's also more of an intellectual way that we approach these things. So someone who's studied music theory and knows that what they're listening to is following a standard chord cadence, versus a physicist who says, okay, this is following the standard prediction of the law of gravity. But wait, this spot over here is different. Oh, wait, this chord over here is unexpected. So having this intellectual understanding gives you a different type of insight. And it's also important, just as is kind of a more intuitive or even emotional understanding.
Cool.
Yeah,
Okay,
thanks for asking about that. That's really important.
yeah. I even watched your jazz video on your YouTube channel. I think that was in 2016 when you were still an undergrad at Yale. Yeah.
Very
Okay.
flattered.
Yeah, I actually Google you on your own website, and then I found that there is a link to your YouTube channel, and that's how I managed to see the videos.
I'm glad you were able to Google my website because always working on that search engine optimization.
Okay. So that's all for our questions today. And at the end of the interview, can you raise a question to the audience and maybe, try to let them think about?
Sure. I guess I would ask the audience, what don't you know, and what other people don't know? Because right now in the age of Google and ChatGPT, you can get the answer to many questions instantly, and it's often a very good answer. And knowing things is becoming less important now. But I think the role of the scientist or the philosopher is to still find questions to ask and knowledge that's really not known. And I think the more you study, the more you learn that there's fundamental things that we're still missing. So I would ask anyone who finds this interview is to start with themselves. Like, what don't you know? And what couldn't you figure out from Googling?
Yeah. Okay. Anyway, it's really nice talking to you today, and thank you so much for your time, Doctor.
Thanks for your interest.
Yeah.
Thank you. Bye.
Thank
Have
you.
a good day.
Yep.